I should say if you do get shocked instead of when you do get shocked, but it's almost inevitable. You may get touched with a little electricity from time to time. And oftentimes your reaction to it can do more damage than actually being shocked itself. Falling off a ladder, pulling your hand back away into a sharp piece of metal or into something moving can definitely be more damaging than the actual getting shocked part itself. So, and last but not least, do not defeat safeties. They're there for a reason. They protect you from liability, and they also protect your boss, as well as others that may come in contact with the equipment. So it's pretty important that we always leave safeties, whether they are for electrical purposes or thermal limits or any kind of safeties, we need to leave those intact. They were put there for a reason. Some of the items we're going to be talking about tonight and topics we'll be going over throughout this class are what is electricity? We are technicians. No one's asking us to design a new system. We simply need to be able to determine if a circuit, what it's doing and how to make it operate the way it's designed to. So we're going to be talking about what is electricity, how and why does it move, what your meter's telling you. The basic electrical circuit, we'll be building several of those. Basic principles of electric motor, and basic electrical component operation. Now there's many more electrical components other than what we're going over tonight, but this kind of give you a good solid baseline for what you're going to find on pretty much all of your equipment out there. And hopefully we can take some of the mystery out of all of it. So let's get at it, everyone. Like I said, if anybody does have questions, speak up in the chat. Ethan will probably try and answer you if it's in the chat, or always, if that doesn't work, just wave for my attention and feel free to pipe up and unmute yourself and ask a question, because chances are if you have a question, a lot of people will. So at a very basic level, electricity is nothing more than transferring electrons from one place to another. This happens because of pressure differences. Just reason anything moves. Air moves because of a pressure imbalance. If you look at the illustration we put up here, basically these are just marbles lined up in a pipe, and the pipe is full of marbles. If you pushed another marble into the pipe, you would get one to come out the other end. If you pushed two marbles into one end of the pipe, two would come out. Wouldn't necessarily be the same marble that went in, but it's just kind of an exchange. The pipe's only going to hold so many at a time. And with that transfer of electrons, the more force being used to push on the one going in, the one at the other end will come out with the same force. So it's not only transferring the marble itself, it's transferring the pressure. These are just some basic illustrations to help you understand that. Now, at a molecular level, and I'll try to stay away from a lot of the real atomic level stuff of why all this works, but at an atomic level, we're basically dealing with electrons and protons. Electrons have a negative charge, and protons have a positive charge. Protons exist within the nucleus or very center of the atom, while the electrons move around it. The electrons are what we need to change places. Now, the atom is happy when it has the same number of electrons as it does protons. It's called what we would say is in balance. When it's out of balance, by having not enough electrons, try to pull more towards it because it would have a positive charge. When it's in balance, it has a neutral charge, same number of protons and electrons. If it had too many electrons, it would have a negative charge. So not enough electrons positive, not too many electrons negative. Just reverts to the charge of what is more within that atom. As you can see here, each of these atoms has 4 positively charged protons and also has 4 negatively charged electrons. Therefore, the atoms are all in balance, and none of the electrons will really want to leave the atoms that they're with. They're all just perfectly happy to staying where they're at. And so in electricity, we need to disturb that balance. And there's several ways we can make that happen. Disturbing that balance can happen due to magnetism, such as passing a conductor through a magnetic field. We can do it with chemicals, such as in a battery. We can do it with heat. This is similar to what you'd see whenever you're working with like a thermocouple or a thermopile. And of course, photovoltaic, where we're doing it with light. Now, the atom on the far left wants to get rid of an electron. It has a negative charge. So it wants to push away its extra electron. The one at the far right of this doesn't have enough electrons, so it has more of a positive charge. Now, the electrons are the only thing that's actually going to move within the electrical circuit. So as you can see, if you have a negative electron, it's not going to want to go towards something that's more negative. So in that respect, when you think about it, the electron is going to go towards something more positive, and therefore electricity flows from a more negative source towards the more positive. A lot of times people think that's just the opposite. Everybody thinks, oh, electricity flows from positive to negative, like in your car battery. It's actually just the opposite. And this is why. It's the electron that moves. It has a negative charge. It wants to go to something more positive. So electricity moves from a negative source to a more positive point with relation to it. We'll get into that here shortly, but basically, if you look at what I put up here on the screen now, it's just talking about potential differences. When we have a potential difference, it's a difference in pressure. Keep in mind, both these charges could be on the positive side. We could have a difference between a +2 and a +8, and the potential difference or pressure difference between these two would be 6, even though they're both coming from a positive number. You could also have it between two negatives, or a negative and a positive. If you went between -2 and +8, the difference between them would be 10. These pressure differences are always going to add together to make up the total difference in charge. So if you look at it like this, we're talking about this +2 here. I don't know if that makes a mark for you guys or not. But if we go between this +2 here and a +8, we would have a difference here of 6. But if we went from this 8 over here to a -2, then our difference would be 10. So that's just our pressure difference on how they'd want to move. So hopefully everybody's keeping up here pretty good. Not seeing any questions so far in the chat. So it's pretty basic stuff so far. Another way to look at this would be if we had two balloons, one with 5 psi and one with 1 psi. Now, in this state, we have something blocking the flow, right? So the electrons are not going or the air in the 5 psi balloon is not going anywhere. It's simply static. It's at rest. It wants to move, and given the opportunity, it will, but there's nowhere for it to go. So they all just sit there. Pressure inside the balloon isn't going anywhere. It's just like electrical voltage. Voltage is not movement. Movement is the potential. It's static. And that can be tough to get your head around at first, but I think the balloons kind of help, or the air pressure in those two places helps explain that it's not going anywhere. It's just a pressure, and it wants to move if released. Another way you may want to think about it is water that's pent up behind a dam. If it gets a hole or a place to go out, it will. That's basically the same thing as potential energy. Voltage is usually signified with the symbol E or sometimes V. These are all designations for voltage or that electrical pressure. And just like we thought, if you release the balloon pressure, the pressure would equalize. Now, we said pressure would equalize, not volume. And therein lies the difference. It has nothing to do with the volume here. It's strictly with the pressure. That's what's going to equalize. So hopefully this is kind of helping everybody get their head around voltage and why we need pressure differential to get it to move. If both were at the same level, it doesn't move, plain and simple. So far we've talked a little bit about a state of balance. Gone through it pretty quick here. It's a state of balance is always sought in nature, whether it be temperature, pressure, any of those. The pressure is always going to want to seek balance. Electrons have a negative charge and protons have a positive charge. When out of balance with too many electrons, the atom itself will take on and try to push away the excess electrons since it has a negative charge to it. When it is out of balance on the positive side, it's going to try and pull electrons towards it. And the total difference adds together between these 2 points, and that is our voltage or potential difference between those 2 points. How's everybody feeling with this so far? Anybody got any questions there? Not seeing anything here in the chat yet. Alrighty. Everybody's doing okay. We'll keep going. Now, a path for electrical movement is what is actually provided with conductors. Conductors are made out of materials that allow for electrons to be transferred through them. Conductors don't store electricity, they don't create it. These materials made out of copper, aluminum, steel, gold. There's a lot of other elements that all can be conductors. Items that do not allow for this transfer to take place or try to stop it from taking place are what would be our insulators: rubber, glass, plastic, things that we use to insulate our wires. Now, there are some other materials that will allow for this transfer to take place, but it's not all that easy for it to happen. So they have resistance. These items make up the resistors that we utilize. When the electrons are pushed with voltage through these materials, it takes a lot of work to do so. And it may help to think of this like a restriction in a pipe with water flowing through it. Both those pipes on the outside of this, if that was a pipe there and they could carry 20 gallons per minute when the water was at a pressure of 100 psi, but the restriction in the middle, where it's neck down, would only carry about 5 gallons per minute. Well, you'd only get 5 gallons of flow through this pipe. And so if you think about it like that, that restriction is what's going to regulate our flow. Okay. Now, in electricity, we call this restriction or resistance to flow. That's our ohms, right? Every circuit's going to need to have some kind of ohms. It's what keeps the flow within check. Much like how the pipe resists the flow of water, electrical resistance resists the flow of electrons. This restriction is given to us in ohms. That's the measurement designation. And with a given amount of pressure, it will allow a predictable amount of flow. Any functional circuit, though, must have resistance. Otherwise, the electrons would just try to run crazy. They all go for the exit all at once, and it'd be kind of a stampede. Now, if you have a certain amount of resistance to flow, and you increase the pressure, seems pretty logical, you would get more flow through that restriction. The same pipe that would only carry 5 gallons per minute at 100 psi, if you increase that pressure up to 150, it's not going to flow about 7.5 gallons a minute. So it's a good way of thinking about how that voltage or pressure, in conjunction with a fixed amount of resistance, our flow can change. If we change the pressure, you're going to get more flow, or less if you decrease the pressure. If you increase the resistance, it's going to decrease the flow. Decreasing resistance obviously makes sense. You would get more flow. One way to think about that would be like the valve, water line. Now, when we talk about flow, okay, we've talked about volts and ohms already, and the ohms is our resistance. Well, amperage is our flow at a very basic level. Flow is basically about that number at the top, which is like 6.28 times 10 to the 18th power. That's the number of electrons that are being transferred past one point every second. That is 1 amp of electricity, 1 amp of flow. Most components have some sort of a rating as to how much flow they can handle. And if you exceed that, that extra flow is going to cause a lot of extra heat buildup, more than what the component's actually designed to handle. And eventually it will cause damage to that component. Now, you're either going to see that rating either as I, which is typically in equations what we utilize. You may also see it with a rating and an A next to it for amps. You may see it designated with RLA, which is rated load amps or run load amps. That is how much that component is designed to carry. It could run at that level or less flow than that, inevitably, for as long as it wanted, and shouldn't have an issue. It will not cause any damage to it. So pulling its rated amp draw is not going to cause an issue. It's when we exceed that amp draw that we start getting excess heat. And excess heat is going to start breaking down that insulation we talked about. That insulation starts breaking down, and then all of a sudden things start shorting across through that insulation, and we get unintended paths for electricity. An unintended path is a shortcut or a short. And everybody is, I'm sure, familiar with short circuits are not a good thing. So some other amp ratings that you may come across would be LRA, or locked rotor amps. Now, locked rotor amps just means that the motor itself is not able to turn. Most frequently, this is given with motors, and the shaft is physically seized for some reason, either external or internal to the motor. But if it can't move the shaft, it's probably going to pull locked rotor amps. It won't do that for very long, usually only a few seconds, and it will usually trip off on a safety, such as the thermal overload inside of a motor. We'll get into those a little bit later. Now let's look at how all those volts and amps and resistance, how they kind of all work together. Like I said, it's a predictable relationship between these three things. Now, volts is designated generally with the E, or potential difference between these 2 points. That's E, that's voltage, right? Our electrical pressure. I, like we already mentioned, is standing for our flow, our amperage. And R is standing for resistance. It's an easy way to think about it. If you put things in a fraction form, 1/2, $1 divided by 2 people, you'd get 0.5. It's 1 divided by 2 in a fraction form. Same thing. If you took your voltage divided by your resistance, that's how much flow that it would allow to carry through that circuit. You could also take your voltage divided by your amperage, and that would tell you how much resistance is within that circuit. And of course, if you took your amperage times your resistance, your result would be how much potential difference or pressure we would see. Now, resistance comes in another form, and a lot of times people get questions about what they're talking about when they hear the word impedance. Well, impedance is nothing more than resistance during operation. When we're measuring ohms, we have to have a fixed amount that we can measure from. And we'll talk about this when we get into the meters a little bit later, but you need a circuit to be unenergized and isolated when you're testing ohms. And if you've ever tested the resistance on a motor and then tried to do Ohm's law, you'll find out that it really doesn't work right. Something's missing. What it's missing is the impedance. You'll actually have more resistance while it's in operation than what just strictly measuring the ohms and plugging in Ohm's law would make you believe that there should be. You won't have more resistance while it's operating. That's what they're referring to when people talk about impedance. So don't get too shook if you come up with the wrong number at that point. That's probably what you're running into is impedance. So when a specific amount of pressure is applied and pushing electrons through a measured amount of resistance, we'll get a predictable amount of flow. If you know any of two of these, you'll be able to determine what the other one is though. And right now I'm going to kind of show you a little bit about how that's going to work. If I can get my computer and everything to cooperate here. Stop sharing. All right. So what you're looking at here is just very basic, some resistors up here, a couple of switches here. We have our neutral coming in from our cord tied into this. These are all just 120 volt neutral here because of this jumper right here. All of these are tied into our 120 volt hot or our L1 line. In addition to that, we have a 40 VA transformer. We'll talk about the VA and what that means here in a little while. Here's our 24 volt common or C terminal that you would typically see on a furnace. And of course our 24 volt hot or coming from our R terminal. We have I'm not sure if you can see that, we have a 3 amp fuse here though. And that's just protection, protect our circuit, right? Up here we have some basic resistors, 225 ohm resistors, these two green ones, and then we have 5 10 ohm resistors. So very basic circuit, we're going to go, or it's going to need a few basic components to it. We're going to need a source. We're going to need a switch to control our circuit. We're going to need a load. There's the resistance to control our amp flow. And then we're going to need a return back to the return side of our circuit. We'll get in more into the circuits, but I just kind of want to go through this and show you how this is going to work. Basically, we're going to start off with our 24 volt source. We're going to bring it over here and go to a switch so that we can control the said circuit. Come out of our switch, and we're going to go to a load. From there, we're just going to give it a return. Now, I'm going to measure this, and I'm going to try and put this meter up here where everybody can see it. Now, right now, this is still isolated. It doesn't have, it's not a functional circuit. It doesn't have a return path yet, and our switch is off. We are still isolated. We set our meter to ohms, and right now it says open line, OL, meaning there is no path. Good practice for you guys to get into if you're not real familiar with electricity is don't let your tools cause you to make wrong assumptions, okay? So I'm just going to test my tool by taking OL, no continuity, and I should have almost 0.1. I would say these leads are good. If you start getting your tools, start getting a little age to them or something, meter leads start breaking down, you may notice that you either get OL or real jumpy ohms at this point when you put the two together. If that's true, it's your tool. And don't let your tool cause you to condemn a component that's actually not the problem. It'll make you make wrong assumptions. But if we go across this, we can see here, you can see my meter there through my hand. Should be able to see that right now we have about 24.8 ohms of resistance through that one. We'll just go ahead and measure all these while we're here so everybody can see what we got. This one's reading 25 even. Now, resistors are also rated with a tolerance range. These are all well within tolerance so far. 10.2, 10.1, 10.2, 10.2, and 10.2. It also wouldn't surprise me if, as these are in use, as they warm up, if that resistance were to change. So sometimes you'll get a little bit of fluctuation. Another rating that you want to think about when you're doing something like this is each of these resistors has a 100 watt, and we'll be talking about watts here shortly, capacity. If you overload it, you're going to overload the resistor, and it'll probably run us into some issues, as in it won't last very long. Go buy a new one if you let the smoke out. All electrical components run on smoke, right guys? Once you let the smoke out, you can't put more back in. So we're going to shift this over to volts now because we're going to go ahead and complete our circuit. So we have our source. We're going to our switch, coming out of our switch, going to our load, and we're missing coming out of our load, giving it a return. Okay, now the circuit isn't energized yet. And if we go from our source to our return, we would see we have 28.2 volts. Pretty typical of what you'd see on a furnace, right guys? If we went from our return and went to our switch, we'd also see we have 28 volts yet. And if we went to the other side of the switch, now we have 0. So that would tell me we've got voltage up to our switch, but not coming out the other side. So our switch is open, right? It's like the drawbridge open. Electricity, like cars, can't go across an open drawbridge. So if you went across your load, this is where it's open. That's where you'd see your potential difference. We're going to work with these a little bit to make sure everybody's getting to this point, but close our switch, turn our circuit on. Now we have no voltage drop up, no potential difference between these 2 points of our switch, right? Now we still have our voltage difference at our source. All of this is still just conductors coming through our switch. Our load in our circuit is always going to take up our potential difference. Right now we're seeing 25.9. What changed? Well, this also changed, 26, so really about the same there. But when the circuit was off, you'll notice it had 28. Why did our voltage change? Anybody got an opinion on it, or I'll give you a few minutes to think about that. Am I overdoing my circuit? Is that why we can't keep all our voltage there? Well, we're pulling 1 ohm or 1 amp of amp draw of flow through there. So 1 amp of flow through these wires, and we have 26 volts, we're getting about 26 watts, right? So if you take that 26 watts, and I know this doesn't seem like much. Everybody thinks, oh, low voltage, right?
Sean in the chat says it's under load.
What's that?
Sean in the chat says it's under load.
He would be right. As you put it under a load, things change. Now, this is only 1 amp of low voltage power, low voltage pressure going through it, right? Everybody thinks, oh, what harm can that do, right? Let me show you a little bit. This is just a thermometer hooked up to the meter here. And if we put this down on, coming up pretty quick. We're already at 220, almost 225 degrees. I'm gonna let that go for a minute. So I want you to see how hot these guys get. This is with 1 amp of electricity. And everybody seems to disregard things when it comes to low voltage and think, oh, we don't have to worry about any electrical codes. It's all low voltage. It's not going to do any damage, right? Low voltage can certainly burn your house down. I'm sure many people out there are familiar with the furnaces that have a low voltage igniter. Ever seen a Honeywell smart valve? Those things get glowing red hot and they work off low voltage. So I was actually trying this out the other day, so I didn't bore you guys to tears while you wait for me to do this. And I actually saw this thing up over 445 degrees. And this is not something that's designed to generate heat. It's a resistor. But as we create electricity flow through a voltage drop, we will always create heat. That heat is what breaks down that insulation if it's not rated for it, on our wires, on our windings, all these things. Now, like Ethan said, we are putting this transformer under a load, and so we see our voltage fall. It's not uncommon to see that. Where it becomes a problem is when we start overloading our transformer, okay? We're going to be getting into that here shortly. But if we do our math on this circuit we've built here, you'll see that from we went to our switch, just like we see in the diagram. Oh, I'm not sharing it yet with you guys, so. Sure. Now you guys should be seeing the circuit that we just built here, right? We have our electrical source, R. We're going to a switch, which is closed at this time. We have a 25 ohm resistor, and we have a common return, right? Ohm's law predicts that if we had 25.6 volts, 1.04 amps, we'd have a resistance of 24.6. Pretty close to what we measured, but not exactly. And like we said, that's really not that uncommon for things to change a little bit when they're in operation. That's that electrical impedance. So when you guys hear the term impedance, don't get too shook by it. All we're talking about is electrical resistance during operation. I'm just, I know you guys can't see me, but I'm actually just measuring that temperature again. Oh yeah, she's getting warm now. We stop sharing here again. As you guys can see, we're well up over that 300 degree mark, 350, and still climbing. So as you see, these can quickly get pretty hot. Does that show up all right, Ethan?
Yep.
Great, thank you. So don't let the fact that it's low voltage lull you into a false sense of security that you will do no damage. You can certainly still burn somebody's house down with low voltage. Any questions so far? How's everybody feeling with all this? My heater ever quits. I know how I'm heating my house. It's getting mighty toasty here. Switches have voltage drop across. Yeah. Closed switches have no voltage drop. We'll be diving into that a little bit more here as well. But hopefully everybody's feeling pretty comfortable with all this so far. Like I said, if I start passing anybody up, please speak up so that we can get you caught up to where you don't find the rest of the class not as useful. Like I said, everything here is going to be building on these simple points as we move forward. So I don't electrocute myself. So this was a basic scenario, number one, that we drew up here. That's what we just built on the board. Okay. Now, some of the oddities in resistance and all. If we look at this, keep in mind, resistance only has an effect or causes a pressure drop or voltage drop when there's actually flow of amperage within the circuit, just like water. If the flow were stopped on the discharge side of this pipe, you'd see that the pressure after the restriction would be the same as before the restriction. It's going to equalize. Just the water, as the water pressure in this pipe would equalize. But once you introduce flow, then that restriction has an effect. And if you plug that into Ohm's law, it actually makes sense. If you do your actual voltage, your measured amperage, and you had 0 amps, well, anything divided by 0 is going to be 0. So you have 0 resistance. It's actually OL, but the way it works out, you don't have any effective resistance at that point because you have no flow. So any resistance there is basically neutralized. Okay, we're going to basically build this circuit now so that I can show that to you, okay? And we'll be testing it. We're going to, if you look here at this, at what I've drawn up here, we're going to start at the source, go to our 25 amp or 25 ohm resistor, come out of a 25 ohm resistor and go into a 10 ohm resistor. Come out of that 10 ohm resistor, go into our switch, come out of our switch and go to our return. Now the electrical circuit really doesn't care where we put the switch. Where we put the switch has more to do with making things more safe. So we're going to stop sharing again, put you back over here to watching our little panel. Get everything plugged in. Go back to volts. And show you that once again we do have voltage here. 28 volts. Now we're going to start at our source. We're going to bring power to our first load, 25 ohm resistor. We're going to come out of our 25 ohm resistor and go into our 10 ohm resistor. Here's our first 10 ohm resistor, right? We're going to come out of our 10 ohm resistor. We're going to go into one of our switches. Out of our switch and give it a return. Now, it's pretty much commonplace to every circuit that you're ever going to deal with. We have our source. We're going to have our load and conductors. Going to have maybe another load in series with it, which isn't really normal for loads and circuits. And then we're going to come into our switch and come out of into our return. Okay. Now, again, we start off here, right? 28 volts. If I went across my entire circuit, I would follow this coming in here to the first side. I'd see I have 28 volts yet. I have 28 volts here. I have 28 volts going into my second load. 28 volts coming out of my second load. and 28 volts going into my switch. As you can see, each of these loads, both of these loads, there's power at each of them, right? There's voltage at each of them. Are they functioning? Many people might think yes, but actually no. I can prove that by measuring amps here. We'll see there's 0 amps, no flow. You don't have a return yet. You have to give it a complete path. So if we look at it, what we were talking about earlier though, if you went from our testing from our return side, we'd see that we had voltage all the way up. We basically have no voltage drop anywhere through here. Once we engage our flow, closing our switch, now you're going to see as we come to our switch, we have 0 and 0 because they're on the same side. Your load or your resistance within your circuit, or loads plural, is always going to take all of the voltage potential or pressure that is there. It's going to divide it up proportionally between how much resistance is there. So if we went across this first load, see, we actually have only 18.7 volts across it. And if we went across the second one, we actually have 7.6. So what did our transformer stop? No, we're still getting 26 volts there. It divides up the voltage evenly. Together, our circuit, with all the resistance or loads in the circuit, are going to take up all of our voltage. Now, most of our loads are rated for 24 volts. As such, when they're rated for 24 volts, hit that not enough times. There we go. Our loads being rated for 24 volts, they're actually designed to start working at 24 volts. Okay, so if you have a low voltage contactor that's rated to work at 24 volts, or a gas valve, that's where they start working. If they're not getting enough voltage or don't have enough of a voltage drop across that component, they're not actually going to work the way they were designed to. Like I said, we usually don't put 2 resistors in series in most of our functioning circuits that we work with, and that's because we need it to be able to get that 24 volts or more, right? That's where they start working. And anything less than about 28, 29 volts, you're probably in good shape. Where this comes into play though, if you have resistance, you will have a potential drop. Doesn't mean it doesn't matter if that resistance is supposed to be there. Could be that you have a bad switch. So keep that in mind because you can lose some of your voltage. And we'll get into that a little bit more as well later. So how are we doing, everybody? Everybody keeping pace here? We're right at the top of the hour. And I think it'd be a good point, give everybody a good 10-minute break, use the bathroom, get something to drink, whatever you need to. And so I will see you guys at 5:10 my time, or 10 minutes after the hour, wherever you are. Pause that recording there right at 10 after, so time to get started at this again. Alrighty, so if everybody's doing okay so far, we'll be diving in a little deeper here now. But what can we do with all these Ohm's law and things we've been talking about so far, right? Doesn't really have any effect on your job, you may think. Only engineers need that stuff. You hear a lot of excuses why people don't put the time into learning that and see what it can do for them. Well, let's look at it this way. If you had a system measuring 27 volts across there, right? You've got a 3 amp fuse on this circuit off of your transformer on your board. What is the lowest resistance that you could have on that circuit that would be able to keep that fuse intact? We can simply use Ohm's law and see that if we took that 27 volts and divided it by 3 amps, you'd come up with about 9 ohms of resistance. This would indicate that if you had any less resistance than that, it would cause more than 3 amps to flow and your fuse would open up, right? Just a matter of plugging it in and doing the math, right? Remember, a fuse is just a conductor though, and it's designed to melt if too much heat is present, and that heat is actually created by the amp draw. So conductors aren't made to have resistance, but we can overload a conductor, and when we do, it's going to create heat. Like we said, conductors shouldn't be the resistance in our circuit, and if they are, we're going to run into some problems. This is why you'll see that places like Ugly's book of electrical references, they're going to tell you in there, and your building code standards are going to tell you in there that you need at least this size, X size wire to carry this many amps. That's the purpose behind it. You wouldn't try to run a 120 volt circuit with 18 gauge thermostat wire. It's not rated for it. Okay. The conductor itself, the copper, electricity doesn't really care about if it's rated for 18 or 120. Well, whatever type of circuit, the copper only has so much flow capacity to it. It can only carry so many electrons per second, the amp draw. Now, the part where the voltage comes into play when they're talking about conductors is the insulation. The insulation actually has to keep that voltage from escaping and creating a short. So the conductor is what size it used to size our amp rating, and the insulation is used to size our voltage for the circuit that we're using it on. Conductors and connections should not have resistance, but just like a 2-lane highway can only carry so many cars, so it is with wire size. So what do you think would have more resistance, a loose connection or a tight connection? Because connections are simply like a wire nut between two wires or a spade connector on a terminal. That is part of your circuit. That's carrying amperage, right? So if we have a loose connection, is it going to have more resistance, or a tight connection? You can formulate that in your mind, and hopefully you already answered it. Resistance creates heat. Okay. If you have a voltage drop and you have amperage flowing through that voltage drop, like in a loose connection, you are going to create watts. You're going to create heat, power. Okay. Just like a resistor that we talked about in our circuit. If you have a voltage drop, you're creating power. You're doing some sort of electrical work. We're going to be starting to get into watts here shortly, but just as a little preview to it, you can see that each watt of power that we create is going to create about 3.412 BTUs of heat for each watt. So you can simply, it's a matter of taking that 3.412, multiplying it by the number of watts, and you can see how much heat is going to be created within our circuit. And that's what we were measuring when we measured that temperature of that resistor. Now, when you measure across the point in the circuit, you'll find a voltage drop, right? Resistance. That's what we were talking about there. And just like we saw in that last picture, generally, if you see something like that, we'll go back to it here. If you see something like this where you have burned wire right next to a connection point, chances are you have a poor connection, because that poor connection is going to create resistance. And A watt is simply a measurement of electrical work being done. And it can very easily be calculated. It's simply E times I. That's going to equal power. Okay. E stands for volts. I again stands for amps. So volts times amps is going to equal watts, or power, electrical work being done. You can use this equation just as we did with Ohm's law. So watts is going to be equal to amps times resistance. The amps is going to be equal to watts divided by volts, or volts would be equal to watts divided by amps. Simply a matter of plugging in the numbers. If you know any two, you can quickly calculate the other one. Being that amps and volts are also used in Ohm's law, you may need to use Ohm's law to get to the either I or E that you do not currently have, and then be able to calculate to your watts. Using that watts and calculate that into BTUs being created. I think there's a test out there, Nate, and they actually do that for certain kW heaters, kilowatt heaters. How many amps are you going to be drawing? It's not uncommon to see questions like that within those tests. So this is really pretty basic knowledge, and it's pretty simple to remember. If you can remember that we changed the spelling of ear to EIR, you can fill in that circle, and you can fill in pi, PIE, you quickly remember Ohm's law and Watt's law for the biggest part that you will need them. There are other equations, I'll show you those here in a little bit, but most of the time, just remembering that EIR, ear, and pi will get you by in most situations. Now, what is all this telling us, all these equations? Well, it's simply telling us what we expect or predict to see with our meters, okay? If you don't know what you expect to see with your meter, then your meter isn't going to tell you anything. It's just numbers on a screen, honestly. So if you can't think in your mind, what should I see here, before you put your meter on it, to tell you, okay, is this switch open or closed? What should I see across these 2 points? Remember, your voltmeter is simply telling you potential difference between the 2 points where you put the 2 leads, right? That's all it's measuring. Much like a manometer, a dual port manometer measures pressure differential between 2 points. Voltmeters measuring electrical pressure between 2 points. That's all it's doing. If you have a voltage difference between 2 points and you provided a suitable path, you will get electrical flow. So if you look at this situation here, we have 2 meter leads, black one and a red one. Black is generally going to be designated as common. Red one is going to be generally our positive. If we put them on the same point in the circuit, it's measuring the same thing. A 9-volt battery, both on the negative terminal, there's no pressure difference there. Is that telling you that there isn't any electricity there? No. So even though your meter says 0, it doesn't mean that there isn't electricity there or some sort of voltage potential there. There's no difference between the 2 points where you put your lead. And this is really important that you guys understand this. Understand what your meter is telling you. It's telling you the difference between the 2 points where you put your leads. Okay, so hopefully everybody lets that soak in for a little bit, because like I said, that's really key to understanding what your meter is telling you. Okay, if you're extending a point by putting a conductor from there, just as we saw, going all the way to a switch, for instance, it's just an extension. That's why they call it an extension cord. You're extending your points from your source and probably your return. So hopefully that makes sense for everyone. We'll get back to meters in a little bit though. Right now, we just want to look at that Ohm's law thing, make sure that everybody's up to speed. Volts is equal to amps times resistance. Amps is equal to volts divided by resistance. Resistance is equal to volts divided by amps. And it's all that equation is telling us, and Ohm's law is telling us the relationship between volts, amps, and resistance. By doing the math, we can see what the increasing voltage with the same resistance presence will cause more amperage. By increasing resistance, we will cause less amperage. Or volts stay the same, and we can vary it with resistance, or we can vary it with the voltage. Increasing pressure with the same resistance, you get more. So beat that horse enough. So in order to have a functional circuit, you pretty much trace this through any circuit you're going to be working on. It's going to have a source, conductors or path, a switch. You're going to have a load to control it, to run or do work. Switch is going to control that, and we're going to have a return. So source, conductor, switch, load, and return. These are common to any circuit that you're going to be working on. You just simply need to determine what that component is going to be doing. And it's also important to understand, is this a switch or is it a load? Because it's greatly going to affect, as you've seen, what we're going to see with a meter going across a switch versus going across the load. Okay. Don't worry, we'll be getting more into electrical circuits and having more fun with those in here in a little bit. Let's talk about the source a little bit. Source and return. This is where the voltage difference originates for the circuit. Remember, electrons are basically lazy. Without a reason, they don't want to move. So this is where we get that potential difference. This is where it's being originated. Generally, it's coming from your power company. Here in the United States, we run on 60 cycles per second. We'll be talking about cycles here shortly. L1 to ground, though, or L2 to ground, we're going to have that 120 volts of pressure for our potential difference, right? Another place you might have a potential difference or source and return would be like in a battery, like in your car, okay? You're going to have something, though, to where that circuit originates for your source, and then you return back to the other side. Conductors. This is what we can carry the transfer electrons on, the path the electrons have to follow. Now, paths are usually intentional, but we do have to be careful not to create unintended paths. This is what you would consider a short. It's a short circuit, a shortcut for the electrons to take. Because remember, electrons are going to take the quickest and easiest path to get to the return. The lower the resistance, the more they're going to flow that way. If there's no resistance, they're all going that way. Loads. Now, you guys spoke a little bit ago while we were on break. Talked a little bit about loads, but loads are basically what we're powering to do some sort of work. Remember that whole Watt's law thing. This could be in the form of a light bulb, motor, resistive heat element, coil of wire to create a magnet. Loads have resistance, creating a voltage drop. The voltage drop across that component, amps flowing creates watts with that voltage, and therefore work being done. All these things are measurable. And quite simply, some loads are more expensive than others. A light bulb's a lot cheaper than a compressor motor. But in the end, if you're feeding it the correct voltage and it doesn't operate, replace the load. Short of a safety being open, obviously, or something to that effect. But if I feed a coil of wire trying to create a magnetic field to close a relay or something, if I feed it power and it doesn't do what it's supposed to, you probably have a defective load and probably needs to be replaced. Just some light bulbs are more expensive than others. Now, when we're talking about resistance, we always want to keep in mind, and unfortunately in Larry and Ethan and in my instance, we often see it, we will ask somebody about resistance. What's the resistance measure here? And they'll say 0. And they may actually mean OL, that their meter's telling them. Well, if you look here on this scale, infinite resistance versus 0 ohms resistance, Those are completely opposite ends of the scale. And remember, when we're trying to help you, or you're thinking about it yourself, we aren't on site with you. We can't see what you're seeing. So if you tell us it has no resistance, that's not the same as infinite resistance. So do try to be specific on that. You'll see on this slide, you have your meter going out and right back to it. You have no resistance. There's nothing to slow electrons down. Versus in the second one on the right at the top there, you'll see we have measurable resistance. And at the bottom, we will say open line or infinite resistance, right? So hopefully everybody understands and takes the time to designate the difference between those. Now in this scenario, we have 3 resistors in series. Remember, those resistances always cause a voltage drop, and that resistance is going to add up through the circuit. All the resistance in the circuit will always take up all of the voltage. They'll divide it up proportionally. But if you have one that is infinite resistance, it will take up all the voltage. So more than one resistor in series will divide up the voltage proportionally to the resistance that they have. The larger resistor will have the larger voltage drop. But if you measure it across all the resistors together, like we have at the top bubble there, you'll measure your source and return voltage. Let's see if I can get this to come up for you guys. So if we go between R and C, we would have our 28 volts. This point here and this point here, this is just wire between this point and C. It's an extension of our return. This point on the far left is the same as R. It's just an extension of that source. So it makes sense that if you measured from between that end of coming into that first 10 ohm and coming out of that 25 ohm resistor, you're still going to read your source voltage. If you don't, you have other resistance in there, right? Now, as electricity is flowing through this circuit, it only has one path to go. So any amps coming in are going to have to be, this is the same as the amps going out. You could measure the amp flow anywhere within this circuit. And if you had 6.2 amps going through the first one, obviously you'd have 6.2 amps going through the last one, right? With these voltages at the bottom here, 10 ohm resistor, you're going to divide that up and that 28 volts up. You're going to get 6.2 voltage drop across the first one. The second one is also a 10 ohm resistor. You're going to get 6.2 volts drop there and 15.5 volts dropping across that 25 ohm resistor. Okay. Most of you have probably done this in school where you had to take these and build these circuits, measuring this and getting used to how it's dividing up your voltage. Okay. If you only have one load, one resistor in that circuit, it's going to take up all of your voltage. So hopefully this is just food for thought and reminder for everybody. When you're hooking up your meter on voltage, you're putting your meter in parallel to the circuit though, right? So your meter isn't a part of the circuit. If you are measuring amps, if you want to count all the electrons, you need all the electrons flowing through your meter, right? So then you're putting your meter in series with it. Now, here's a pretty basic way, similar to how you'd be hooking up for most of your flame sensor readings, right? You put your meter in series with the flame sensor. When you do that, you're actually making your meter a part of the circuit, right? And just like if you wanted to count all the cars going down a road, you need them all to come through the gate, the toll booth. Or if you're counting everybody going into a ride at Disneyland, you'd be counting all of them going, all the people going through the turnstile. You wouldn't want to just count some of them. You wouldn't get an accurate count. So it is with your meter, okay? So that might be a good way to kind of think about it and help it make sense. You're trying to count the number of electrons going through. Now, another type circuit you may have would be parallel circuits. Just like our meter, even if you put your meter here, it would have another way around it. It's the same way you're hooking up your voltmeter, right? So parallel, you have multiple paths. Some electrons are going to come down through resistor number 1. Some electrons are going to go down through resistor number 2. And some of the electrons are going to go through resistor number 3. The wire here on the bottom, on this positive here, going back to this battery, it's all the same. It's just wiring between the positive terminal and all the positive points on these resistors. So it's just an extension. So there's no difference between that conductor and where it comes back to our battery. Same thing on the negative. The negative terminal, if it's just wire in between or conductor in between, you're not going to see any voltage drop there, right? Every one of these loads is receiving that 12 volts from this battery on the left. On our series circuit, we'll have only one path, right? So there's one path from start to finish. There's only one way to get through here. And then, of course, you can hook things up in a combination. Multiple branches, each branch having several, one or more resistor, okay? If they have, so this leg is a series circuit, but it is in parallel to the second leg down in here, which is also in parallel to this third leg. So hopefully that's a review for everybody. If not, please raise any questions you may have about it. Now, there's going to be some rules about how voltage works in the different types of circuits, basically between series and parallel. Okay, so here's an easy way to remember those. If you have, this is going to be the rules for how watts, volts, amps, and resistance behave in a parallel circuit versus in a series circuit. Power, watts, it's always going to add in either series or parallel. Volts, but also going to add in a series circuit. Amps is going to stay the same throughout the circuit, and resistance is going to add. If we add up all the resistors within that series circuit, we're going to get the total resistance for that circuit. Easy way to remember that is reciting your. Well,
hey, Keith, I have a question for you.
Yes, absolutely.
So going back to that, your that
Yes.
parallel indications of multiple. I have a problem with a fan coil. I can't find, I mean, I've tested all my leads. I've tested everything else. Positive, great continuity of coming in 24 volts, 208 for a fan coil unit that's in my quarter system, but it's not turning on. So, I mean, how do I test the transformer, I guess? Can I with the series of connections in the circuits?
Actually, you may want to hold on to that because we're going to be getting into relays here in a little while with the
Okay.
and it may actually answer your question.
Okay, sorry, I kind of excited and
Nope.
learning. So sorry.
Perfectly fine. Like I said, let's get to that part. And if it doesn't answer your question, or if you can't answer your own question, then we'll chat about it a little bit more. How about that?
Perfect.
Okay. So, if you can spell PEIR as PEIR, power, volts, amps, resistance, And then remember, adds stays the same, adds. You've already remembered how your watts, volts, amps, and resistance act in a series circuit. In a parallel circuit, though, we're going to have adds stays the same, adds joint. Now, joint's a little bit weird.
Keith, let me stop you right there a second. We got one other person that's got a question.
Certainly.
Leche, you want to unmute yourself?
Lost my chat box here. Did he put it in the chat room or?
No. Why don't we keep going?
Okay. Well, if it reoccurs to him, please feel free to speak up. Okay, so joint resistance. Joint resistance is actually defined as the reciprocal of the sum of the reciprocals of each resistor, which in an equation form looks like this. Sounds a little messy, right? Okay, so let me break this down. The reciprocal of a number is basically its inverse. If you were to take any number and divide by 1, it's that number. So 2 over 1 is 2. So the inverse of it would be flipping it over. It'd be 1 over 2. So 1/2 would be the inverse of 2. So simply taking 1 divided by the resistance gives you the reciprocal of that resistor. So if you think of it as resistor A, resistor B, and resistor C, 3 different resistors, 1 divided by resistor A, and then add that to 1 divided by resistor B, add that to 1 divided by resistor C, all of those added together would give you a decimal point. Take that result, 1 divided by that result will give you your joint resistance. Okay. Now, joint resistance is a combination of multiple paths. Just like if you added another lane to a highway, anytime you add another path, it's always going to be less resistance than the lowest individual resistor. So it's a good way to do a little self-check there if you're ever trying to come up with that joint resistance. Thankfully, you don't have to do that math very often, but it's good that you understand how to do that. So if anybody needs to, feel free to jot that equation down. Your total resistance, or R total, is going to be 1 divided by that 1 over RA plus 1 over RB plus 1 over RC, and then working out the math. Take you out of this now. Stop sharing. I'm going to build a couple other circuits here so we can kind of see what we mean by that. So, killed our power. Just gonna do a couple of checks here. This is what I meant at the beginning by test before you touch. It's always good practice. Make sure it's safe to touch. So, if I was to go across this, volts AC, and I have 0. Talk about that AC and DC here in a minute, but this is voltage AC that we're working with. So right now we're going to build our source, which is 24 volt hot. We're going to go into a switch. We're going to come out of our switch. We're going to go into resistor number 1. Come out of resistor number 1 and give it a return. Now, that's a simple series circuit, right? Now we're building a parallel circuit. So in parallel, or another path, would be taking and adding into another resistor. I should probably do this in another color, make y'all's life easier to understand this. So in parallel to this load, now we're going to have another load. There's two separate paths here. If we start at our source, a low voltage source coming into our switch. Coming out of our switch, we're going in here, or some of the electrons may go through here, because I put this wire in between these 2 points, right? So this is the same as this, same as this. We're going to be measuring this with a voltmeter if you're having trouble following that. And then each has path back to return. So electrons can go from in either direction, right? So at this point, we have our 28 volts, which is what we expect to see, right? Now, if we go across our switch, right now this switch is open, right? So this point is the same as our source. We have 0 voltage drop between those two. There's no difference. Even though these are what most people would consider electrically hot, our meter's saying 0 because our meter isn't telling us that there's electricity there. It's telling us the difference between these 2 points. That's all it's telling us, right? If we go across our switch, we will see our source voltage. Infinite resistance, open. It's taking up all of the potential difference, all of our voltage. We then close this switch. Now we have 2 circuits in parallel to each other. So this point is the same as this point. And we'd expect to see 0 volts, right? If we went to the other side of our switch, we would expect to see 0. And pretty much what we got. If we went across that first load, we're going to see that we have our source voltage. And if we go across our second load, we should see our source voltage. And we do. So each of these is getting source voltage. This is what you're going to typically see in most instances because you're going to want each individual component to get source voltage. So if you're thinking about this on a furnace, your gas valve, for instance, is going to be in parallel to other circuits, right? Hopefully that's making sense for everyone. And if you were checking how many amps were going through just this second load, you would see 0.9. So just shy of 1 amp. If you were seeing how much was going into our total circuit, you'd see 1.9. Just like we expect, our amperage added together, right? We're getting just shy of 2 amps for both circuits together, each one having just shy of 1 amp on each leg. So just like we predicted, amp draw adds. Hopefully that helps everybody. Now, we got 1.9 amps flowing through this, right? And here's where it kind of starts getting interesting. 1.9 amps, I have a 3 amp fuse. My fuse should be in good shape and not experience any issues, right? But if I was to take that 1.9 and getting back to Watt's law, if you think about it, right? Everybody remembers Watt's law, that was volts times amps. Well, voltage, 23.6, just shy of 24 volts, right? 24 volts times 2 amps. How many watts is our entire circuit carrying here? It looks like it's going to be about 48 watts of power that we're putting out here on both circuits combined. Watts always adds. Now, if you look right here, this is a 40 VA transformer. Well, we just said we just measured it and did the calculations. We're putting in 48 watts, right? So what's beginning to suffer here? Well, remember, this is supposed to be a 24 volt transformer. Now all of a sudden, we're only getting just shy of 24 volts. Our voltage is starting to suffer because we're overtaxing our transformer. So even though our fuse is staying intact, we haven't exceeded the 3 amps, but we are overtaxing this transformer. This transformer being overtaxed will cause the windings inside the transformer to get hotter than they're designed to. The insulation starts breaking down, and our transformer is pretty much destined to die a slow, miserable death. So when you guys are adding in circuits, maybe you're adding in a humidifier on the system and thinking, oh, I'll just use the transformer that's in there. Well, maybe you can do it. And as you can see here, we're going to keep our fuse intact. We're well below what it's rated at. But this is where you end up with transformers that every year it's costing you a transformer. What's going on? Well, it's because what we're asking it to do is beyond its capabilities. This is only a 40 VA transformer, and we're putting almost 48 watts through it for an output. So if you're having a system that keeps eating transformers, you might want to look at that and do the calculations, because there's no safety in here that's going to tell you, hey, you're overdoing your transformer, you're overtaxing it, right? The only thing that's going to tell you that is you keep eating up transformers. So keep that in mind. You know, as a technician, it's kind of our jobs to do this part, do our homework, and make sure that we're using a transformer rated for what we're trying to power and do with it, right? So hopefully that helps with some questions like on that fan relay. Any questions on that part so far? Is everybody good with that? Understand what we're talking about when we're talking about the amp rating of a transformer versus what we're asking it to do? Let's see if I can get my chat window to pop back up here.
Got nothing in chat.
All righty, so let's look at some other components here. Capacitors. Now, capacitors are simply an electrical storage device, similar to a battery. Except the only difference is they release all their energy that they've stored all at once instead of slowly over time. It may help you to think of this like a flash on a camera versus a flashlight. The flash bulb on a camera, just everything goes all at once. All the energy is released in one quick burst. Versus flashlight wouldn't do you much good if it all just lit up and then died immediately. Unless you're trying to make a strobe light. Capacitors are rated in farads, and a farad is typically, and farads are simply a measure of how much electrical energy they can store. Typically used in HVAC equipment, the ones we use are rated in millionths of 1/1,000,000th of a farad is 1 microfarad. So when you're talking about MFD or the backwards U, those are backwards U is a symbol for micro, and micro is 1/1,000,000th of whatever you're designating it. Micro amp, like in a flame sensor, would be 1/1,000,000th of an amp, or 0.000 to get to your micro. Capacitance works similar to resistance, except it's flip-flopped. In series, it's going to be joint, and in parallel, it's going to add. Okay, so just like you did the joint resistance a little bit ago, the same formula works out for figuring out capacitance. But if you hook capacitors in series, it's going to be their joint capacitance instead of adding together. You need to hook them in parallel to get them to add together. Okay, so we're going to use this equation real quick here on the screen. we have a 5 ohm, 8 ohm, and 10 ohm resistor. Now, if you took 1 divided by 5, it equals 0.2. 1 divided by that 8 ohms is going to equal, if you did the math, 0.125. And 1 divided by 10 would obviously be 0.1. We add those together, so 0.2 plus that 0.125 plus that 0.1 would give us a total of 0.425. Now remember the reciprocal, we need the reciprocal of that 0.425 to get to the actual resistance or capacitance, whatever your measuring joint are. So 1 divided by that 0.425 would equal 2.353. Now, remember, I said that little trick to self-check yourself. Our total or joint resistance would be lower than the lowest. So 2.353 is lower than our lowest resistor, which is 5. It gives me a good indication that I'm on the right track here and have an accurate answer. If you come out with a number though that's higher than your lowest, you did something wrong in your math. Like I said, this same equation works with capacitance and resistance. Okay, so let's look at using our voltmeter. It's probably most used out of your diagnostic tools. Okay, you're going to see the squiggly line there indicating alternating current, AC, alternating current voltage, right? AC voltage doesn't necessarily have a plus and a minus all the time. They cycle back and forth, right? You're also going to see on your meter, or most meters, hopefully yours included, where it will say RMS. Now, RMS stands for root mean square. Basically, it's the effective voltage. If you look at what we're talking about on this wave sign here, the sine wave, our voltage goes up and then comes back down, goes into the negative territory, peaks, and then comes back to our 0 point. Our 0 line in the middle means 0 volts. If we peaked up here, say 130 volts, the vast majority of the time that this was running through, the mean voltage would be much lower than that. So it's hard to really do much work for that 1/1000th of a second that you may be up here, or even less. So our average or mean voltage would actually be where this green line is. That's what an RMS meter is telling you. It's telling you that mean voltage, which is much more usable in forms of doing work for what we have to do. So an RMS meter is not telling you the peak voltage, it's telling you the effective voltage. So hopefully that makes sense for everyone. It's really important though that you use RMS meters or you will come up with really strange readings and your Ohm's law won't work out right. It's going to really lead you in the wrong direction. If you're looking for 24 volts peak voltage and not mean voltage, your components probably won't be operating the way they're designed to at 24 volts peak because we're looking for that mean or average voltage basically, right? So this is a typical sine wave that we'd see with all of our electrical equipment. And we're talking about AC, like we said. When you think back to the beginning of all this, we talked about how electrons flow from a negative to a more positive, right? Well, here, in this sine wave, you can see L1 went positive. So electricity is actually flowing from that more negative or neutral post towards L1. As we cross over the line, now all of a sudden those electrons are going to start turning around and going back the opposite direction. So they're alternating, going back and forth. And this is where we get the term alternating current because it's alternating flow, so running back and forth through the wire. First it goes one direction, then it turns around and goes the other direction. Now, in contrast to that, we also have DC voltage. DC means direct, means the electrons are always going directly from its more negative point to its more positive point in one direction all the time. When we're talking about just doing work, such as with a contactor or gas valve or something to that effect, AC works fine. When we're trying to transmit data, though, you're going to find that most things that are transmitting data are actually working on a DC current, or DC voltage potential. And that's important because if many of Train's furnaces out there, you'll measure between D and common. And if you measure an AC, it's going to say 0. And you're just not measuring in the correct voltage. Switch your meter to DC and you're going to see 12.9 volts, something to that effect. And that's that data stream. So not only do you have to look in the right place for the voltage, but you do have to have your meter set to the right function. If in doubt, check both. If you think, hey, there should be voltage here, and you're not sure which one you should have, check both AC and voltage, because you may have a data stream or a DC voltage, and it won't show up on your you're trying to measure with that. So keep that in mind, everybody. It's important that we set our meter to the correct function. And it's part of our job to be able to realize that. And so, like I said, if you're in doubt, just switch it over to the other one. Just make a quick check, okay? As we talked about earlier, that backwards U stands for milli, or 1 millionth, or I'm sorry, micro, which is 1 millionth, and seems kind of backwards, but M actually stands for milli, which means 1/1000. So a milliamp is 1/1000th of an amp, and a microamp is 1/1 millionth of an amp. Big difference in between them when you look at them in the decimal form. 0.001 amps versus 0.000001 amps. This is why when you're looking for amperage on your flame sensor, you aren't going to pick it up with an amp clamp. It's a pretty small amount of electron flow to get down to that micro level, right? So understand the difference between those, and your meter should have microamps as well as milliamps or millivolts. So understand, it's important that you understand the difference between those. Okay, so now we're going to start talking about that voltmeter again, right? We're going to start looking for where is that potential difference. If you look in this scenario that we have up here, we'd see our potential difference obviously across our source. And we should. If you don't have it there, nothing's going to work, right? Where else might you have it? What if you went over here to this area of your switch? Well, this is just wire all the way back to our source, right? So it's an extension of it. So if I took my red lead and put it over to the incoming side of our switch, I would expect I still see 120 volts. If I didn't see that there, I know that there was a break in the circuit somewhere between those points. If I went to the negative side of our circuit, we'd see 0. Just as we predicted, we'd see our 120 volts. Now, if I switch my black lead to being on the outgoing side of our source, like we said, there's no difference there. We'd expect to see 0. Hopefully everybody's taking the time to understand that, and please let us know if you are struggling with that, because this is really going to be key for you to understand your diagnostic procedures. If you went across both these sides, even though you have resistance in between, you have an open switch, there's no flow, no amp draw, this resistance of this light bulb is irrelevant. There's no flow, so the resistance becomes irrelevant, right? All that pressurizes, just like the pipe we talked about earlier. It's all at the same pressure. Our potential difference here would be across our open switch, right? We'd see source voltage, even though there's resistance there, because the resistance, again, there's no flow, so the resistance becomes irrelevant. Open switch, you went across the load, we'd see no voltage drop, right? And then when we close our switch, now we see our source voltage across our load, and our load should be operating. If our load is getting source voltage and it does not operate, go get a different light bulb, right? Even though it might be a compressor, motor, whatever kind of load it is, if it's getting source voltage and doesn't operate, you probably need a new load. Now, going into our load, right in here, to the incoming side of our closed switch, well, this is now just a conductor. Switch shouldn't have resistance. It's just a drawbridge. Drawbridge is closed, our switch is closed. There shouldn't be any resistance, so it's just an extension of our source now. Of course, you go across our switch and we'd see 0 volts drop because there's no resistance there. Alrighty, we're good on time. We're right at the 6 o'clock mark. So before we jump into the rest of this, why don't you guys take another 5-10 minute break, and then we'll dive into some more of this. And you guys, okay. Remember when we talked about resistance being in series, everybody? Resistance may not always come in the form that you intended it to. What I mean by this is, we look at this, we have a source, a switch, a load, and a return. But we measure our voltage at our load, and all of a sudden we don't have quite as much as we had at our source. Well, if you go back to Ohm's law and how resistance adds in a circuit, it becomes pretty relevant that, or pretty apparent, that obviously we're losing voltage. We have resistance somewhere else in the circuit. And when we find that resistance, we'll find that they add together, makes up our total voltage, our source voltage again, right? Now, this may not seem like it's overly important, but when you think about it in this respect, most of you have worked with motors. Most people understand that motors actually pull more amps to do the work that they're designed to do, okay? And Ethan gets into that and everything when he gets into his motor class, and I think he has some advanced diagnostic that includes motor here in a few weeks. But if you're lacking voltage, you still got to do the same amount of work, same amount of watts. We're going to pull more amperage. Amperage creates heat. So you get a switch that starts getting some carbon buildup, starts developing some resistance. You're going to have a voltage drop there, which is going to make less voltage available at your load. Less voltage, it's going to pull more amps to get the same power output. More amps creates more heat breaks down your windings. All of a sudden, that switch starts costing you a motor. Now, switches come in many forms, and we'll talk about relays later, but it could be as simple as a contactor, and maybe you're running a compressor. Now, all of a sudden, because you let that contactor get to the point where it has far too much resistance, it starts eating up a compressor. Well, you just let that $50 contactor or switch cost you a $500 compressor. So when you're doing your checkouts and monthly or annual maintenance on this equipment, might be worthwhile looking at those contactors and seeing if we have an excessive voltage drop across there. Because if you have a voltage drop, you have resistance. You're losing voltage there. It's going to steal some of the voltage and cost you a compressor eventually, or at least cost you in the form of higher amp draw. Hopefully that's helpful to some of you guys that may be seeing motors going out. It might be worthwhile looking at those connections as well as those switches, because all that should just be a conductor, and conductors shouldn't be the resistance in the circuit. So hopefully that starts coming together for everybody. We look at this example here, right here, we find our missing voltage at our switch. Another common failure in using meters that we see, this load, as you'll see on the left, we have L1, goes through a switch, going to a motor, goes back to L2. Well, L1 to L2, we can presume by looking at this that this is either a 208 or a 240 volt motor. It's a circuit that works on 240 or 208 volts, right? So we also frequently see people where we've all done it, start checking the ground, looking for voltage to see where your circuit is failing at or open at. And if you test to ground anywhere on this circuit, where would you see? Well, if you go L1 to ground, you're going to see 120 volts. If you went L2 to ground, you're going to see 120 volts. And so if you tested here, see 120. Here, 120. Same here. Here, coming into the switch, or at L1. All these points, you would measure 120 volts. What did that tell you about your circuit? Absolutely nothing other than don't touch it. It's not safe to touch, right? Now, this is great if you're seeing if it's fine to work on, but as far as diagnostic, it's not really showing you anything useful at this point, right? You need to test your voltage differential or potential difference to your return and source. So now if we compare to our return of L2, we'd see coming out of our motor, 0. I would assume going out at our source, we'd see 240. We'd see going into our switch, 240, just an extension of L1, right? All the way up to the end of our switch here. And then if you checked here, you'd see 0. No amp flow, no amp draw through the circuit, so no amp flow. Resistance is negated. And you would find that by testing to our return, we'd see that our circuit is open at this switch. Now, this switch could be a safety or an operational switch, but we know that that switch is open. So don't get in the habit of testing to ground. Test to your return. It's going to be really important for understanding when you're diagnosing and getting to where you have accurate results, because just like we showed you, everywhere to ground we had 120 and would have. Now let's talk about that amp draw. Okay, we talked about a little while ago about wiring a meter in to measure our amp draw. That's fine and dandy, except it's sometimes inconvenient. Most of the time we're going to be using an amp clamp, okay? And an amp clamp is picking up a magnetic field and simply translating that to current flowing through the wire. So they're just a more convenient way for us to use and measure that amp draw. They're usually generally pretty accurate, but they do have their limitations. As long as you understand that it's picking up the magnetic field, it's going to increase your chances though of being accurate. So you want to make sure you're not holding your amp clamp right next to a motor or something else that's creating a strong magnetic field, because that's also going to pick up that magnetic field. And that's going to influence your readings that your meter is telling you. Now, when you look at this, if we put our meter measuring amps going through one time, it's going to show what the amperage is in that meter or going through that wire. If we looped it through there, we would see it's counting each one as it passes through the first time and the second time. 2 loops, multiplying it by 2. So amp clamps simply interpret magnetic fields around the wire and translate this into current flow. Clip it around the wire, away from any strong magnetic fields, and it picks up the magnetic field that's being generated by the flow in the wire, translates that, and gives it to you as your amp draw or amps flowing through that wire. Now, generally, amp clamps don't work that great when you're really low in flow. Like if you're measuring less than 1 amp draw, 1 amp of flow, it's probably not going to be overly accurate. But you can use what we talked about earlier and get a more accurate reading. Now, I don't know about y'all, but I find it easiest to multiply by 10 because you're simply moving a decimal point over, right? So one little trick you may want to consider would be when you're measuring your amp flow, if you're having a really small reading, let's throw together a circuit here from our source, going into our switch, out of our switch, into loops of wire. Still conductor, not affecting anything. Into our load, out of our load, give it a return. Things zero out. Turn on our circuit. Have our loop of wire here, right? This is 10 wraps of wire. So if I measure this, I'm seeing 10.4 amps. But this is multiplied by 10. We actually measure down here 1. Not only are we counting it 10 times and making our reading 10 times higher, we're also 10 times more accurate. So something to keep in mind when you're measuring those small amp draws. Might be using a 10 wrap. And I just made this out of some 14 gauge wire, wrapped it up, go anywhere on here and be at that 10 wraps. So I know already what I'm going to see there. I just have to move the decimal point. Makes my life easier, right? Like I said, it may not be useful when you're measuring large amp draws, but when you're measuring those smaller ones, it can definitely make your life a little bit easier. So, everybody get that? No questions, should be pretty simple. We're simply counting those same amps 10 different times, right? Now, here's a little thing. Electricity and magnetism are intrinsically linked. If you have one, you get the other. Okay? If you have magnetism, you are going to create a potential difference of voltage. If you have current flow, you are creating magnetism. And like it or not, there it is. Sometimes it works against us and creates impedance in a circuit. Other times we can use it. If we pass a conductor through a magnetic field, though, it makes the electrons want to move. We talked about this when we were talking about creating voltage. So this is one of the ways we use the magnetic field to create the voltage. You just saw that we can also use that magnetic field that's created from that current and measure it. Now, keep in mind I said pass through to create that voltage. So just putting a conductor inside of a magnetic field doesn't do much for us. But if electrons are flowing through a wire, it creates a magnetic field, amp picks it up. If we go back to where we were looking at the sine wave, and as that sine wave expands and contracts, we're going to make a magnetic field that's expanding and contracting. When we make it through the first half of the sine wave, though, we're going from L1 being positive and our neutral wire being negative. Left-hand rule says if you wrap your fingers of your left hand around a coil of wire that electrons are moving through, if you point your fingers in the direction the electrons are moving from negative to positive, your thumb will be pointing at the North Pole. Okay. Now, as we move through our sine wave, all of a sudden, remember the electrons reverse direction. Poles flip-flop also. And then our North Pole would be at the bottom or down towards the opposite end. So we would make a magnetic pole in one direction and then a magnetic pole with the north in the opposite direction. We're going to play with that a little bit here in a minute. We use that though in transformers. Remember I said transformers rated in VA, which is volt amps. Now, volt amps is the same as watts or power, right? The reason they don't say that a transformer is rated just in watts is simply because not all electrical loads are created equal. Electrical loads sometimes some are not as efficient as other electrical loads. Now, strictly resistive load like we've been working with here has a power factor or an efficiency factor of 1. Think of it as 100%. Okay. What you put in, that's what you get out. There are some electrical loads, such as using a magnetic field to turn a motor. It may not be as efficient as that resistor, and that power factor has to come into play with this. So the way that all works out is now we have our VA is actually going to be equal to our watts divided by our power factor. If we have a power factor of 0.8, think of it as 80% of the efficiency of 100%. So 0.8 would be less efficient, about 80% efficient, as our 100% efficient power factor. Best power factor you're going to get is 1. Okay, that means 100. So our input power on our transformer and our output power of our transformer is going to be the same. Can't really destroy power. We can only convert it. So where this comes into play is if our power has to be 120 going in, it's got to be 120 going out, right? The way they work a transformer is using that magnetic field to induce a voltage into another winding. So this is where that AC sine wave going in, peaking out, going back to 0, basically turning off, turning around, going the other direction and peaking, and that magnetic field flip-flops. Think of it as growing and shrinking, just like a bubble or a balloon. It blows up and inflates and then deflates. Now, we get to where we want to be for our secondary voltage in our turns or our ratio of turns. So the output voltage compared to the input voltage is determined by the ratio of turns on the primary side on the left and versus the second number of turns on the secondary side on the right. Since power doesn't get destroyed, merely converted, as voltage is stepped down, amperage is going to step up because power or watts is going to be E times I. so that the power that comes in has to stay the same as power going out. So
Hey, Keith, you want to switch your camera?
actually, let me go back to screen share.
That'll make more sense.
Yes. Sorry about that, guys. Okay. So if we come into our primary side with 120 volts and we want to step down to 24 volt output, we need to induce a magnetic field that will cut across our secondary winding. Our number of windings ratio, 5:1, is going to take our voltage from 120 down to 24. Since our voltage went down, our power has to stay the same. Watt's law says that as we step down voltage from 120 to 24, we're going to step up our amperage. And if we're drawing 5 amps on our secondary side, it's going to induce that load through the magnetic field into the primary side. And it's going to pull 1 amp on our primary side. Okay. Got a pretty good slide that's going to help you with that here in a little bit. First, I want to go back to that VA rating. We talked about how it has to be able to support the load that it's doing. If you're overtaxing it, our secondary winding most of the time is going to turn out okay. Maybe, maybe not. Now, when people build transformers, they build them with that specification, how many watts it's supposed to put out. Any more than that, you're going to have more amp draw. More amp draw, more heat. Well, they also don't like to waste material. Everybody builds things as least expensive as they can and as compact and light as they can. So primary winding is generally going to be thinner, even though it has less turns on it than our secondary winding, because the secondary winding is carrying more amps. So they don't need to make the primary winding all that heavy a gauge of wire, because it's only pulling 1/5 of the amps that our secondary side is in this instance, right? They're rated with a power factor, just like we said. Power factors is actually a shift where things aren't as efficient. Our amp draw sine wave in green is not peaking the same place that our voltage sine wave is. When we get less efficient, we actually have to pull more amps to get these two to where they'll equal out at our power. This is why you see transformers rated in VA and not just watts, because it depends on the load that they're hooked up to. The one on the right here, you can see the amperage and sine waves are in phase with each other. Now, if they're in phase with each other, that would probably indicate that your power factor is at 1, or just strictly watts, volts times amps. We don't have to worry about figuring in that power factor to get that accurate measurement of what we're putting out. Now, if you watch closely in this, when we start out from our bottom, we're going to go through this a few times because there's actually a lot happening in this slide. On our incoming side, we're putting in our voltage, right? We start off going positive at the top and negative at the bottom, and then it turns around and goes the other way. Well, if we're positive at our top, negative at our bottom, our electrons are starting out here at the very beginning of this and flowing that direction. If we do the left-hand rule, you'd see that the North Pole is down here at the bottom. As we go through this, as you go through its phase though, remember the electrons turn around and go the other direction. If they turn around and go the other direction, our north and south are going to flip-flop. As they do that, electrons go the other direction, left-hand rule. Now we're looking at our North Pole being up. So that flip-flopping as we go through our sine wave here is causing that magnetic field to expand and contract. See if I can get that to play again for you guys. Expands and contracts. Flips over, expands and contracts. That magnetic field is cutting across the windings on the secondary side of this coil transformer. That is inducing. When we hear inducing, remember, think through magnetism, we're inducing a voltage on the secondary coil, and that is making an AC current sine wave on our secondary side with a voltage proportional to the number of turns. It's a long explanation for we're stepping down our voltage, but we're going to step up our amperage because power has to stay the same. Everybody good with that? That is basically the understanding of a transformer, how to make it work, or why it works. Transformers come in many types. One of the common ones probably everybody handles on their truck is a multi-tap transformer. What they mean by a multi-tap transformer is typically we can put one of several voltages, but we have options depending on the wires that we choose. We hook up the correct wires, we can still get the same voltage out of the secondary side, but it's just how many windings that we're going to use of it. So if you go into an OEM transformer, such as the one on the left here, you would see one primary winding, one secondary winding. If you go to the one on the right, you'll see that there's multiple options. If you have a higher voltage, you just need to use more windings. So this example, this would probably be common to any voltage that we're going to use it to. If we're going to use it on a 120 volt circuit, we would use this winding. Electricity is going to flow through these wires only, and we'd have this many turns compared to our secondary winding. If we're not using it on a 120 volt system, say 208, you need to use it on this tap. So where we can use all these coils to step down and get to 24 volts. And same if you get down to 240, of course, we need even more windings, right? What this is going to do for you basically is give you multiple options, but this takes a little more work on your end. You have to measure the voltage coming in to make sure that you're on the right tap. Because if you stepped down 240 volts at the same ratio that you did 120, you are not going to end up with 24 volts coming out. Same thing with 240 and 208. It's important that you realize that if you only have 22 volts coming out and you have 208 coming in, good chance you may have your transformer on 240. And if you change it, you'll probably get the right voltage coming out. So it's important that you shift that over. You see that fairly frequently on rooftop units where they come set up to either operate on 240 or 208. Have seen it where the electric company actually changed transformers midstream for an area, and all of a sudden people's RTUs weren't working right, and they were basically trying to run on 21 volts on the secondary side instead of that 24. And as we talked about a little bit earlier, those low voltage 24 volt components are designed to start working at 24. So 22 can cause a lot of issues. Contactors can start to chatter, relays maybe not staying closed all the way. Maybe they're not closing as tight. And we end up causing a loose connection at the switch, which, like we learned earlier, causes resistance within that switch. The resistance starts causing arcing, you get carbon buildup, more resistance, and it's only a downhill slide from there until that contactor, relay, or switch starts eating itself. Now, another thing we can do with those magnetic fields is when we talk about magnetic fields, everybody's probably played with magnets when they were a little kid and found out that if you try to put two like poles next to each other, it's kind of hard to push them together. And if you put two opposites together, like a north and a south, they kind of suck towards each other, right? So they're attracted to dissimilar poles, and like poles repel. That is basically what you're going to end up using when you're making a motor. As you can see in this diagram, the south pole's next to the south pole. Well, like you found out when you were a 10-year-old kid playing with magnets, that's not going to want to stay that way. So that south pole is going to be pushed away from that other south pole towards the north pole where it's being attracted. Same thing for the north pole. It's being repelled away from that north pole towards the south pole. Well, in so doing, it's going to turn the shaft, and there you got your basic motor. This is how pretty much most of your motors are going to work. Here in the US, though, remember, this is AC current. We run on 60 hertz or 60 cycles of that electrical signal, sine wave. One cycle is basically going from its 0 point here at the beginning up through here, all the way positive, peaks, comes back, gets back to 0, goes all the way to its peak of negative, gets back to 0. This is one cycle. We have 60 hertz or 60 cycles per second here in the US, which means this full cycle is happening 60 times every second. This comes into play when you start thinking about motors and these poles flip-flopping back and forth and how fast that motor is going to turn. Now, there's a little formula I'm going to show you on the next slide that tells you how many cycle or how many RPMs that motor is going to turn at based on that cycle, right? And so the speed of our motor is going to end up being dictated by the cycles per second of that magnetic field being created, collapsing, flipping over, expanding, contracting, and starting over from there. The other thing that will affect your speed of your motor is the number of poles. So if you look at the one on the right, you'll see that that rotor only has to turn 90 degrees instead of turning over a complete 180 degrees in 1/2 cycle. So if it's only turning 90 degrees, it's only turning half as far as it started off with, which means your motor is going to end up turning at half the speed. That little equation is going to end up looking like this. Your synchronous speed, or the speed of your magnetic fields. If your rotor was keeping up with the speed of that magnetic field, it would be 120 multiplied by the hertz, which here in the US is 60, divided by the number of poles. Now in our first motor back here, the one on the left, we have 2 poles. On the second motor, we have 4 poles. So it's pretty quick math to find out that 120 times 60, you should end up with 7,200 divided by 2 poles. On the one on the left, our motor is going to be running at 3,600 RPMs. And if we do that same calculation with the number of poles being at 4, such as this motor on the right, we're going to end up with half that in speed. Half of 3,600 is going to be 1,800 RPM. So just like we predicted when we were looking at those poles, you're going to see as we add poles, we decrease speed. We'll get more into that when the people get into the motor class here in a few weeks, but basic understanding of a motor there, what's causing it to operate. It's again that magnetic field. We're just using it. Now, resistive loads such as resistors, lights, and heating elements may change as the temperature of the load changes. Generally, as the temperature goes up, so does the resistance. Inductive loads, loads that work through magnetism, work through a magnetic field and are trying to perform a certain amount of work, such as simple motor trying to turn at an X number of RPMs. Motors will actually pull more amps in an effort to maintain their speed, maintain that synchronization with that magnetic field, causing a higher amp draw as the motor is under more of a load. So if you increase the load, you're going to increase your amp draw. Good to keep in mind when you start thinking about a motor and what's going to happen to that amp draw. Say a blower motor in a furnace, you start cutting off airflow. The motor doesn't know how much air it's moving necessarily on a typical PSC motor. It just knows RPMs. So as you start cutting off airflow, there's less work that it's doing. It's moving less air. It's pumping less air through the system. Your amp draw is actually going to fall because it's not working. It's just freewheeling. It's just spinning. When you give it more work to do, feed it more air, it has to push more air. It has to do more work. As it does more work, you're going to see the amp draw increase. So low amp draw on your PSC motor is probably going to be pretty in sync with not having enough airflow, dirty filter, some restrictive ductwork. As you feed it more air, you're going to see a higher amp draw. Okay. So another example that I'm going to show you here, trying to do work and not being able to do it, and how that increases our amp draw. So in this example, we're going to undo our resistive load. Simply going to go to the coil of this contactor. Now this contactor has a 24-volt coil. Hopefully everybody can see that. Close our switch. It should cause this to close our coil, energize the coil, making a magnetic field, pulling the contactor closed. And when doing, it creates an amp draw of 0.3 to make that contactor work. So now I'm simply going to take a pair of pliers and keep this from closing. Our amp draw went from 0.3 to 1.2. So as we prevented it from doing its work, we caused our amp draw to go up. So this is a load being induced through a magnetic field. Just like in our motor here, we're inducing a load through a magnetic field. We talked earlier about capacitors and how that capacitance works with motors. Now, we're just explaining to you here how to make it work the way it's designed. Test a capacitor. It should have X amount of capacitance. You wire it into the motor, and it helps improve the phase angle of the motor, helps it correct that power factor. As you'll see on the motor on the right, we're simply varying the number of poles so we can change the speed. When we look at how the motor is actually wired, though, you'll see that the run capacitor is actually wired in series with the start winding. So the capacitor is actually part of that circuit. If you take the capacitor out, you don't have a complete circuit for your start winding. You'll see on the motor on the right, we have multiple points. The least number of poles would be our highest speed. Highest number of poles would be our lowest speed. Another situation that we use in magnetic fields is electrical relays. Now, electrical relays are no different than the contactor we were just showing. This is a standard single pole, single throw relay. I'll explain that here momentarily for you. Some people get a little confused when we start talking about relays, though, in that, what is a relay? Well, a relay is simply a remote controlled switch. Apply voltage to make a magnetic field. The magnet in turn moves the switch from open to close or vice versa. Easy way to think about this is a monkey. I could make a monkey, train a monkey to stand over there at a light switch. And when I shock the monkey, he'd turn the switch on. And when I stop shocking him, he'd turn it back off. Okay. Pretty simple. It's easy to train the monkey. The monkey's not part of that electrical circuit. He's simply operating it. Okay. That's all the coil of a relay is doing. It's operating the switch. The coil is not part of that electrical circuit that the switch is. It's actuating it. Now, we talked about that single pole, single throw. So your poles are where your incoming voltage is. So in this example, say terminal 3 was our incoming voltage. That's our pole. The voltage can only be thrown out of one throw. So it's a single throw. It can only put that power to one place. Single pole, incoming power, throws are outgoing power, how many places it can throw it to. Now, abbreviating normally open, coils and switchers are generally shown they're at rest or unenergized state. So when this coil is unenergized, this switch is open, meaning that you have to power this coil to close this switch. So this would be a single pole, single throw, normally open relay. Now, like I said, you could train a monkey to do this. However, eventually you're going to get tired of buying new monkeys. They die, they eat bananas, you got to clean up after them. The thing is, if you put too much power to the monkey, you're going to have a dead monkey and smell burning hair. If you put too much power to this magnetic coil, you're going to kill your monkey. Don't kill the monkey. Don't overpower the coil. If your coil is designed for 24 volts and you feed it 120 volts, you're going to need a new coil, need a new monkey. If this were a normally closed relay, single pole, single throw, normally closed, you would see this switch in the closed position. Like I said, they're generally shown they're at rest or unenergized state. So hopefully everybody gets this, that you energize this coil, it activates this switch from being its normal or unenergized state to the opposite. So relays are nothing more than electrically operated or electrically controlled switch. The electricity you're using to actuate the switch is not the energy that's going through the switch. So
Did that clear it up for you, Sebastian?
give him a minute here to get off of mute and find his mute button. He was asking about the fan relay earlier.
I think so.
Well, if he pipes in here, let me know.
Okay.
So this relay that we're showing here on the board has one pole, one incoming power right here, right? It's a single pole designated by SP. It can throw the power to two different places, so it's a double throw. One of those places is normally closed in its normal at-rest state. That switch is closed over to there. If you energize it, the normally closed is then going to open. And that switch is going to come over here, and the power will be thrown to the NO, the normally open contact. Again, this coil is just creating a magnetic field and turning that switch from one to the other. Now, you buy a really high dollar monkey, you can get him to work both hands at once. So this would be a double pole, double throw. So you have two incoming power terminals, each having two terminals that it can throw it to. These two circuits are not necessarily communicating with each other. They might be on totally different circuits. They don't even have to be on the same voltage. But we have two separate switches, right? Energize the coil. Both of them that were green, normally open, are thrown to the energize the coil, and they go from the normally open or normally closed to the normally open. So if the coil is unenergized, our power is going from the blue up to the red, the normally closed. Energize the coil, and the red terminal is no longer getting energy, and it's being sent to the green ones. And this is happening on both switches simultaneously. Hopefully that cleared it up for Sebastian. Clear as mud, right? And that's pretty much it for a relay. Now, another component that you may run across would be a diode. A diode is simply an electrical check valve. Lets current go in one direction only. Now remember, we're back in sine wave here. Our alternating current is flip-flopping back and forth. So you would get half the cycle going through a diode, but you would cut off the bottom half. It's one use for a diode, but it's simply a one-way valve for electricity. Electrons to go through in one direction only, right? You can arrange 4 diodes into a rectifier. And when you put 4 diodes in this configuration, when electricity is going this direction, it hits a roadblock, can't go down, so it can only go up. Hits roadblock here, so it's only got one way to go. Now it's wanting to get back here, but it's going to flow through here, goes through this load, comes back, comes up this way. Well, that's where it came from. Same polarity. Doesn't want to go that way. It wants to go towards the opposite polarity. So it has to go out this way, come back, and get back to our return. The way that's going to look is if you just follow that yellow ball as our electron, you're going to see that the incoming AC voltage current is being sent out and reversed. What's going to happen on our DC side, though, it always goes out the same wire. So we're basically sending it out in AC and going through those 4 diodes arranged in that configuration to be a rectifier. Our output is going to be DC. You'll see this several times in different equipment. So don't be surprised if you see 4 diodes. And they may not look like that configuration, but they will be wired in that configuration. So hopefully everybody kind of sees how that's working there. It's really pretty simplistic when you break it down. Again, they're just one-way check valves for electricity. So we're just controlling where it's going. The last thing I want to talk to everybody about is wiring diagrams. Now, wiring diagrams are often made way too difficult. If I was looking at a road map and I wanted to get from Indianapolis to Fort Wayne, Indiana, this would look like spaghetti, right? There's pretty much no way to tell. So don't look at the entire wiring diagram. You need to look at what portion of it we need. It's just like a road map. If I was looking to get from Indianapolis to Fort Wayne, this is much easier to read. So it is with wiring diagrams. If I look at this, it starts looking like spaghetti, right? And if we stop sharing, go back to here. take a look at some wiring diagrams. This can quickly look like spaghetti. So don't look at the entire thing. This is actually another wiring diagram showing you the exact same thing as what was in the first. Okay, it's just two different forms. Hone in on your wiring diagrams. Use highlighters. If you look here, I've kind of diagrammed out. Our power comes out of our high limit output, designated with HLO, high limit output. Goes out there, goes out through over to the input side of our condensate safety switch. Then goes through our reverse airflow sensors, and I see C note 11 right here. Look at note 11, it actually says downflow models only use one reverse airflow sensor switch. So I wouldn't see two of them there. If I have an upflow, I'd see two of them. Those notes could be important when you're diagnosing. You might be looking for something that isn't there. As it goes through these normally closed switches, you'll see that it comes back through the flame rollout switches, thermal limit, over to the input side, pressure switch 1. Now going back to our series circuit here, if we opened up our reverse airflow switch on our furnace, we would never even see power getting to our pressure switch. This is in series to it. Once we closed this normally open switch, because it's shown in the open position, it's shown in its normal at-rest state, we'd see that then we get power all the way back to our pressure switch input to the board, PSI, pressure switch input. If we have our condensate switch closed, we're going back through our orange one, back to our input here. So look at your inputs and outputs. If you're not getting power back from the pressure switches or to the pressure switches, not getting power out through your inducer input, inducer limit input, you probably have a open condensate, because if this switch is open, you never get power to your switch. Kind of comes back to those things of being in series, but you have a couple of things that break off, right? Don't look at everything. If I'm looking at low voltage problems, say I'm opening a low voltage fuse, remember all these heavy lines are of high voltage. They're all out of the picture. It's like looking at the entire road system of the United States on the map. You don't need to look at all that. Hone in, use a highlighter, look at what's important for what we're using, right? Look at that portion of it. If I was looking at a road map, again, I wouldn't look at every street in the United States. I'd look at how I'm getting what's important between Indianapolis and Pennsylvania, or from high limit output, high limit input to our board. This is going to help you on your reading your diagrams, to where you're not trying to look at everything on there, looking at all the spaghetti. Okay. This even gets pretty messy. Pictorial diagrams help a little bit use it to find out where components are located, but much harder to read than this. These are the same thing. Things I highlighted on this one in pink is the same exact circuit in pink on here. Okay, it's just two different ways of showing it. In a ladder format, a little more easy to read, or more of a pictorial. So don't be afraid to do a little homework on those. I believe Ethan goes into those a little bit more on his advanced class. Now, we were talking about trying to make a circuit with relays, okay? Now, just like this and the wiring diagrams, this can really start to look like spaghetti after a bit. So what I'm going to do here, I'm going to build another simple circuit. We're bringing these off. Try to keep these color coded to where it's easier. But we're going to bring our power in. First off, let's start at the beginning, everybody. We have a power coming in right here, our source. Take our source power, we're going to bring it to a switch so that we can control it. We're going to come out of our switch, bring it to our load. Out of our load, here, and give it a return. Source, switch, load, return. That's the low voltage. On our high voltage is coming in here, bringing it out of our switch side of our relay, and we're going to bring it into our high voltage load. We're going to come out of our high voltage load and bring it back to our return, which is wired in right here. Okay. There are multiple terminals, just like on this end, just as there are on this end. This and all these, it's just conductor in between. They're simply there for convenience. So don't let the fact that there's several terminals confuse you. There's no difference between any of them on this side. All of these are separate from these. These are two separate switches. Coil activates this relay contactor, beefed up relay, closes the contactor and turns on a light, right? I didn't put the light bulb in the picture because it totally blows up the exposure on it. But now we've simply made it to where we close the switch, we create a magnetic field, and closes our switch. We're using a low voltage circuit to control our high voltage load. The low voltage is not part of this circuit of the high voltage, it's merely actuating it. Hopefully that makes sense to everyone. Last but not least, I just want to inform you guys, when you're in the field, I encourage take a look in your free time at fieldtechhelp.com. Has some great videos on explaining electricity, circuits, and many of the products you will come across on Train. It's based on either Train or American Standard. Simply pick the appropriate one there. So again, that website is fieldtechhelp.com. All righty, that brings us to the conclusion of our class. Any questions? This can be called an isolation relay, commonly condenser or furnace accessory. Yep. Inverter boards, I'm guessing he was talking about the diodes arranged in a rectifier. Any questions, anyone, or does that make sense for everybody? And it was kind of a long class, but I think there was a lot to get through in there. Hopefully I made it a little more absorbable and a little more understandable for everyone. But thank you everybody for sticking with me. Hopefully you enjoy the night. If you want to go back to these screen where we showed all the numbers to where everybody can jot those down when you need assistance, feel free to give us a call. Remember, we do these from G.A. Larson at their expense, trying to help you guys out, make your lives easy. So when you get stuck, feel free.
Nathan, the recording will be posted to the website, and be in probably a couple days. So there's a portal on the galarson.com website where you can access all of the recordings that we have under the training tab that's there. We'll also be having the advanced class, which is kind of just a part 2 to this, where we go into a lot more depth in motors and get into some 3-phase power and some other wiring diagram stuff. But that'll be in April, I think second week of April. That's also under the training tab where you guys can register for that. So.
I do thank you, everybody, for sticking around, going through our class with us.
Nate, contactors, that particular contactor that he was showing is a single pole double throw. You could have up to single pole quad throws or triple pole, triple throws, all sorts of different kinds of contactors. So just kind of depends what you're using. But the one that Keith was using is a double pole, single pole double throw.
Yeah, they're pretty common. Everything, but you can use them on anything. It's simply a heavy-duty double pole relay. I'll be hanging out here for a little bit if anybody does have any questions, so feel free to ask.